Anyway, this is our last fish nutrition lecture. I'm going to be sad after today. I tell you, I've enjoyed this. So what we're going to do is talk. This is going to be kind of a whirlwind, because what I did is I'm opening with just a few slides that I put together from some material that I was looking at earlier, and that I think will kind of lead into really the culture and production of the two principal live feeds that are used in larval fish nutrition and larval fish culture. And so there are really a lot of slides, and they're from a fellow that I know. I didn't put those other two presentations together, from Harbor Branch. Dr. Ken is now at NOAA, and I'll like to show you some of this stuff in just a second. But what's interesting is, take a look at the Artemia, which is the brine shrimp. We talked a little bit about that before. So that's, and we're going to go into this in more detail, but these photos are pretty good. So you see the photo on the left, that little kind of winged creature, that's the Artemia, soon after hatching. The cyst that it's hatched out of, you can see the crack in the shell, the cyst. And this here is the organism upon leaving. It has kind of a hyaline shell or sheath around it, real thin, clear membrane that it really breaks away from before it can spread its appendages that it uses to move about in the water. And you can see this is a hybrid striped bass that I worked with some guys a few years ago. They spawned the fish. We were experimenting with some larval culture. And this fish was in the process of metamorphosing, and it was getting close to it. It was still a fry. But you can see its gut here is loaded with Artemia. So this would have maybe 10 or 15 of those little guys in here. Notice this kind of bulb above where its gut is. That's the swim bladder. Okay, just so you know, that's not a bubble. It's not oil, it's not an oil drop, it's a swim bladder. So the fish is, and here's another example. This is another species. I'm not sure what species this is, but it's also getting ready to consume a live Artemia nauplii. And the nauplii is that one of the first couple stages of development. Remember, these are crustacea, and like any crustacean, any crab or lobster, etc., it has to molt or shed its exoskeleton in order to grow. And a couple of things to point out here in this early slide. Notice the color, real orangish or yellowish. And remember, before we talked a little bit about carotenoid pigments, and we talked about yolk, etc. And this is an indicator that the Artemia were full of that high quality lipid or yolk-like material that is in this early instar or the nauplii of the Artemia. That's when it's most nutritious. As it gets older and grows, unless you feed it some sort of a media or nature, it would be feeding on some other live organisms. If you didn't feed it, or if it didn't get any nutrients in it, then it would just kind of it would grow as long as it could, because after a while, after it depletes its lipid store, then it's going to run out of energy and will die. But until then, it's going to keep growing and growing and growing. There will be less and less of that high energy nutrient lipid available for fish, and basically you're going to have just kind of a skeletal, muscular, larger organism that doesn't have the energy nourishment that these larval fish really need. Okay? So again, bottom line here is an early stage, it has a lot of lipid. That lipid has got a lot of essential fatty acids that the larvae need, and this is when it's highly nutritious. So this is an example. I wish I had a color photo. I don't have one. This is one out of a text that I saw. So this is like a close-up, okay, of a larval fish gut. This is actually the notochord. This is the beginning of this backbone, right up here. So this is where the esophagus is coming. The head's going to be over here. And then you see this coiled gut. The important thing is, throughout here, each one of these black things, those are the eye spots of the Artemia that's been eaten. This is a halibut, a marine fish from the northwest rather. And as you can see, in this early stage of development, there's no stomach, and it's kind of pooping out. Although it's a little bit hard to see here, it's not digesting the Artemia very well. Okay, because when it's excreting or pooping out, it's basically a whole Artemia. So nothing's really been masticated well, its mouth parts are immature, there's no real grinding activity in its stomach. So basically it's eating everything it can get hold of, and it's doing its best to digest, but the entire gut is really divided into a foregut, midgut, and hindgut. Got names there at the end. But it's just absorbing as best it can. It's just not very efficient.
Are the Artemia dead?
The Artemia, in some cases, actually are not dead. I mean, they
can survive through.
They will, in some cases, survive through, which I have never heard of before until I was going through this material. And I was like, oh my God, you're kidding me. Because I've seen the Artemia with the striped bass in the early stages be pooped out, pretty much intact, but never seen them alive. But apparently, the author here has had experiences where they would actually leave alive still, which is pretty amazing. So you can imagine it's just not very efficient. Now, a little bit later, and then there's also a new, I guess I've heard about this in the past, but I haven't seen it in such a long time. It's kind of crazy. This author was referring to growth and development in degree days. So that would be degrees centigrade time days after an event. So and I'm just sharing that with you because you may confront this term sometime. And it's, I think, important for the poikilotherms because their development often is predicated on temperature, growth related to temperature, right? If they're growing in a high temperature, they're going to grow faster than a low temperature. So the author was kind of describing the growth of these larvae in terms of temperature degree days. Temperature degree days post-spawn. In another case, it was the temperature degree days post-hatch. Again, I'm just sharing that with you. You might want to that might be a test question, I don't know, but you might want to note that because it's kind of interesting. So here's a fry or larvae, and again, I'm going to use those terms interchangeably. That's just a couple days post its first feeding. 2 days after first feeding. So it's probably been hatched about 10 days. Halibut are a cool water species, and so they hatch over a longer period of time than a lot of the fish that we work with here in North Carolina. And you can see, again, the Artemia are still fairly intact. The gut that we just saw a minute ago, it's coiled here, and this is where it all comes, where all the activity was that we saw before. Now, as it gets a little bit older, you can see that the body is evolving, it's maturing somewhat, the gut is larger, it's more distinct, and now these are the chromatophores, these are the pigmented bodies here, these are not the eye spots of the Artemia. The whole things are kind of spider-webbed out, right? These are cells, pigmented cells. But the Artemia eyes, you can still see some here, right? To show that digestion is not very thorough, but it's getting a little bit better because the waste as it's coming out, again, it's still a little bit tough to see. But here, for example, is an exoskeleton of one of the Artemia, and you can see that the contents are pretty much removed. It's not full of stuff. It's kind of empty. You can see like the outer shell and just a little bit of stuff in the middle, okay? Whereas the Artemia that are intact, that have not been digested very well, you would see this really fully loaded with protein and lipid and whatnot. So a few weeks later, so this is 2 weeks after post-spawn, this is 2 weeks later, the gut is working better. it's becoming more efficient. Then again, as the fish is metamorphosed, halibut's a flat fish, so during this period of development, the eyeball migrates, the fish kind of flattens out, and then you can see that about 39 days after first feeding, the poop coming out is all mixed around, showing that there's more mastication, there's more degradation of the material as it's working its way through the gut. Again, here's the esophagus, the coil, and then out to the anus. Again, the orientation in halibut, as in any flatfish, is going to be a little bit more unique compared to the other species that we've seen, but still it's basically, the concept is the same. Bottom line is, larval fish have unique needs. Okay, the take-home message here is when the larvae fish first hatch, they're tiny. Most of them are really, really small, like a couple millimeters long. The striped bass that I'm going to be working with in a couple days or a couple weeks, they're like as big as your eyelash. So our challenge as fish culturists is not only how do we, find out what are the right nutrients that the fish requires, but how do we put them in a package that the fish can get at? Well, you can see it's kind of a challenge, right? Because shoot, at the very beginning, their gut can barely even degrade or create a situation where whatever it's taken in can even be utilized as a food, right? So it's a challenge. How are we gonna, how are we gonna meet the needs? Well, again, size matters. Number one, size is important. Whatever you're feeding, it's got to be small enough that the fish can take in efficiently. It can't be so tiny that the fish has got to peck around all day to get what it needs, because it would use too much energy searching for prey when actually it needs a lot of energy just to grow. Now, this is an example, again, of some of the Artemia cysts. Artemia has just become globally one of the most recognized organisms to be cultured as a first live food for most fish. Some fish, their mouth gape is so small, they cannot even eat Artemia, and we're going to talk about rotifers in just a second. But because Artemia is so dominant, I really wanted to kind of get your attention on the Artemia. And we're going to cover this a couple times. So we've got the cyst, it's opened up, the nuclei is going to exit. We call this the umbrella stage. Well, actually, this is the umbrella stage. But this first part here, it's going to come out, it's enclosed in that sheath. You can see here, once it exits the cyst, and then it breaks through the sheath. The sheath is kind of like an umbrella. Sometimes they even call this kind of a parachute. It'll jettison that after a while, and then finally it'll be on its own, fairly immature, loaded with lipid. Okay? Okay, let me get to the next presentation here. I was having a hard time combining these. Okay, so let's go to Artemia, because they are the smaller of the two groups. And this is from Harbor Branch, Ken Riley. Super nice guy. He's working for Noah here at the Beaufort Marine Lab. He's an ECU grad, but we're not going to look at this one. Okay, so that's a rotifer. Of course, it's an up-close kind of a micrograph. Eggs are down here. But this is the body that's loaded with nutrients. The skeleton is really a silica covering, and the eggs actually are very nutritious. If you can feed a rotifer that's carrying a bunch of eggs, that's even better. So why do we feed live feeds in general? Well, we've already talked a little bit about this. The main thing is that they're readily eaten by larvae. You could say that they are cleaner to use in a system as opposed to an inert feed because they don't degrade like inert feeds do. Generally, our experience is that, especially in marine fish culture, we've got greater survival. And again, this is just from a microscopic photograph. You can see a whole series of rotifers. It's not very good focus, but there's a whole pile of them there. And there are many different species of many different types of live feeds. We've been talking about the Artemia. There are some larger, this is a type of an isopod, but the rotifer here is what we're going to really be focusing on in this presentation. We've already talked about, rotifers versus Artemia. So size is really critical. Take a look at the prey size that most larval fish go for, 50 to 120 microns in width. Now again, length isn't so important, but it's got to be the right width so that they can get consumed. Generally, fish are attracted by the movement of the organism. So when we feed an inert diet and it's just sitting there, an inert, meaning like a food, like a regular, like a crumb, like something that we make ourselves. Okay? Because it just sits there in the water or just slowly sinks maybe, it's not that much of an attractant. But when it's kind of moving about within the water column, that seems to attract the larvae a little bit more. Again, there are different species of larvae, as we talked about, and you can see how the guts are a little bit different, how the mouth parts are a little bit different. But the bottom line is they need something that's nutritious and of the right size. In this photo, you can see the fry over in the kind of the mid-left area, and all those other little dots, those are all the live food that it's going to have to go for to eat. So what's really important is that when you stock your tank with your live feed, you've got to have enough that the fish doesn't have to swim around all day just to get something in its mouth. Usually we put as many as from like 4 to 20 of these organisms per milliliter, per ml, per cubic centimeter, right? 4 to 20 within that little space. So it doesn't have to spend all its energy hunting for something to eat. And so let's take a look at this. On the left-hand column, there's a list, there are multiple species. You can see the temperature range that they are hatched at and held at during this larval period. And then I think what's interesting is when you look at the egg diameter, you can see like salmon is pretty big. It's 5 to 6 millimeters. You've got a turbo that we were just looking at is about 5 times smaller than that, somewhere about 1 millimeter. So you can see that if you just look at the data throughout this chart, you can see that there's quite a range, which means that there are a range of size of the eggs and therefore the resulting larvae. Therefore, you just can't say, well, I'm going to just feed Artemia or rotifers to everything that I would ever hatch. I mean, this is obvious. Every species has its own mouth size. And this is another example of a variety of different species of fish and the prey width that they use during the first feeding as they're developing. So there's, again, different species have requirements that vary. The other thing that's important, we talked a little bit about this before when we were just talking in general about small fish having a greater metabolism than large fish. And you can see here, look at the demand for food. So larval fish consume more food per unit body than do fish in a grow-out operation. So you have like 50 to 300% body weight per day that you would feed versus 2 to 10%. And I said something about like 4 to 20 organisms per ml. This author is saying 5 to 30, but you get the idea. It's a lot of, the take-home message again is you've got to put in enough food items in the water so that the larvae doesn't spend all this energy just trying to find something to eat. This is an example with southern flounder. With any species that you're going to be rearing, the culturist has got to know, is going to kind of plan out a feeding schedule. And when you're working with the species for the first time, it's kind of hit and miss. You're going to be looking at a schedule, a calendar, if you will, of what the requirements are, and you're going to have to scale up and switch as the needs of your larvae are going to change. Now, with southern flounder, they're not going to be eating microalgae. We haven't said anything really about algae, but by stocking microalgae in the cultural tank, basically what you're doing is you're maintaining an environment for the rotifers to survive from, well, until they're consumed by the flounder. You can see here that the period is identical, right? This microalgae incorporation in the environment is the same as the enriched rotifers. Again, the idea is that those flounder, the microalgae is too tiny for the flounder to eat, but it will be present for the rotifers to consume during this phase when the small flounder larvae are trying to eat, and they're going to really target the rotifers. But after a while, after about day 12, they're going to start to bring in Artemia, and then after about day 21, you're going to use those larger enriched Artemia. We're going to talk about that in a second. So the scheduling here of incorporating larger food items is to correspond with the demands of the larvae as they get larger. Now with rotifers, their population dynamics vary quite a bit. And you've got to have your facility capable of providing the rotifers when the fish need them, and sometimes that corresponds opposite to when the rotifers are at their maximum population density in culture tanks. So let's just take a look here at some of how this is done. So again, rotifers are an excellent, highly nutritious live feed. They reproduce quickly. They're very hardy. They're the right body size for many larvae fish. Again, microscopic invertebrate. The different species do well in different salinities. They undergo asexual and sexual reproduction. I'm not going to go through all the morphology details. You can see they're kind of cool. They've got this corona that's ciliated near the mouth part. Some of you guys have probably seen this in high school biology, right? And you look at, this is a protozoan, and the cilia they're in kind of a sweeping motion that will draw a current of water to the mouth. And the idea is that this is always going on, and they're flipping around the water column, although again, they're microscopic. But you can, under the microscope, see little particles that are drawn in to follow that current, and that's how they collect material to consume. They've got this esophagus coming from the mouth into the stomach, and then there's a whole digestive system by which they're able to utilize those food particles and grow to reproduce. Here's another example there of the corona with the cilia, which are the tiny hair cells, the tiny hair filaments, directing the water current into the mouth. Again, you can see the esophagus. In this photo, the cilia or the mouth are at the bottom of the screen. So you've got the esophagus, and then above that, which is really below it, in general, there's the stomach. It's got an appendage, we call it a foot. You can see they even call other components the toes that are used to attach, although it's usually free swimming. There are marine species and freshwater species. The important thing here for culturists is they talk about, ordering. If you talk to a hatchery manager, you'll say, yeah, I've got to get some L type, or some S type, or double S type. This refers to the basic size of the rotifers. So you can see here 70 to 160 microns, 150 to 220, 200 to 360. So smaller, medium size, and larger. Again, this is all relative to rotifers. But the point is, again, depending, size matters. Depending on the species that you're raising, even in terms of rotifers, size is important. Okay? Generally, you're going to culture them below 35 parts per thousand. What's the salinity of seawater? Does have any idea? Keep an aquarium? It's about 32 parts per thousand. So generally, you're going to want to keep it below 35. Somewhere around 20 to 30 usually is pretty common. Temperature range, say 75, 80 degrees, 27 to 32 degrees C. This is about a 15-hour photo period. It does well, a little bit of variation, moderate pH, fairly neutral, and you want to keep your ammonia levels down. So when the conditions are right, you're going to have a female that's going to develop with eggs. These are all egg packets here. It's not a very clear photo. And there's an example of the juvenile there on the right. I'm not going to go through all the details of reproduction. The point is, it's somewhat complex. And there's a resting form. There's a sexual, there are both sexual and asexual means of reproduction. We're not going to go into all that detail. I think another important point is rotifers only live 6 to 8 days, okay, for females, and just about 2 days for males. Females produce up to, it says 1.4 offspring per day, so a couple offspring per day. Reproduction begins 18 hours post-hatch. Just think of that. 18 hours after it hatches, reproduction takes place. So your goal as a culturist is to try to maintain a really strong, nutritious, positive environment so that you can kick in reproduction quickly. Your goal is to try to get the rotifers that you started with to become, to reproduce quickly and wind up with the concentration that you need in order to feed the fish that you're culturing. Okay? So fast reproduction. 1,000 animals can become 1,000,000 animals in 5 to 7 days. So what do? So usually guys will go ahead and get on the phone with a company like Reed Mariculture. That's not an endorsement, but I'm just saying they're pretty common. They're out of California. You can get on the phone and get up with one of the biologists there and place an order for a culture, a test tube, or a pouch, a sack, that they can send from California, and you'll use that. It's kind of like a starter yeast if you're a baker, right? So you get this starter bag, and you'll go ahead and you're going to have your tanks already, and you'll have the right salinity and the right temperature, and no ammonia, and everything's just all set up. You'll pour that bag of rotifers in there, and you will have already inoculated the tank with some nanochlorops. We'll talk about that microcellular algae. That's what the rotifers are going to eat, right? The rotifers are going to have something in order to grow. So bottom line is you're going to get in your starter, and when the conditions are right, they will reproduce like crazy. And you're going to have usually most of the guys that I've worked with do what's called a batch harvest. So they'll get tanks and they'll rear their rotifers up, and then when the rotifers reach their maximum density that the tank can hold, they can, you can't raise like 1 billion or 100 billion rotifers in a certain size. There's a certain point at which, okay, it's time to harvest them and feed them out to my fish. So a lot of farmers that I work with, they do this in a batch. They'll get the batch up, and they'll harvest them, they'll feed them, and they'll start over. Other facilities do a continuous production Well, they'll harvest a portion out, you know, once the production reaches a certain maximum, then they'll harvest maybe 30% at a time. And that way they just keep the process going. They like that because they don't have to stop. They just kind of go from one tank to the next tank to the next tank, depending on how often they need to feed and how many rotifers they have to feed out. By the time they get to the third or the fourth or the fifth tank, the first tank is at max production again. They haven't had to shut everything down and clean it all out and start from scratch. So the continuous production can be really good. One of the difficulties, though, or challenges, is that you can sometimes get disease to occur a little bit easier. So if your facility isn't really clean, continuous culture can be more problematic. So this shows, for example, a facility where they're raising rotifers in these different containers. The light there is very important for hatching. You have filtration, pure oxygen, capability of adjusting pH, etc. This is kind of a model of a working system. Again, you've got filtration, you've got your growing tank, filter system, etc. And there's a rotifer tank. There's algae in there and rotifers. And again, it just looks like a bunch of mush right now because they're microscopic. There's your algae. Now there's another, raising algae is also a challenge, it can be. I mean, we do it all the time, but there is a company or a couple companies that actually make an algae paste. They can save you all sorts of time. So they'll get algae, they culture these different algae species in large vats, and then they'll remove a lot of the excess algae, condense or concentrate the algae into a real thick paste. In some cases, the algae is live. Usually when it's condensed a lot, significantly, it's no longer, these cells are no longer living, but to the rotifers, it's not necessary for them to be a living cell. And there's some commercial systems on the market, a couple of examples here. Again, rotifer cultures are healthy. If the rotifers are swimming rapidly, again, you want females with eggs. And this is something that the cultures really pay close attention to. If they're going to count the females with eggs versus those without, and if there are like a whole lot without eggs, then that's going to indicate that the system's not working really well. Again, the eggs, we've talked a lot about eggs, right? Yolk, lipids, it's really important. So, and then of course cloudy water. Some of you guys have had aquariums before, right? When the water gets cloudy, is that a good thing or a bad thing? Usually it's a bad thing, yeah. And usually, just so you know, most of the time the cloudiness is due to the presence of bacteria, a lot of bacteria that are actually living on a lot of debris, really tiny particles in the water. And as you can imagine, if the culture crashes, it's going to probably have a bad odor because it's just decomposing. Okay, so at Harbor Branch, they'll go ahead, fill a dry tank with seawater to about 30 parts per thousand salinity, put some chlorine in, add some sodium thiosulfate to neutralize it, and then they want to clean the tank cleaned right off the bat. Then they're going to go ahead and add the inoculated rotifers we were talking about at a rate of about 100 to 150 cells per milliliter. Again, use aeration, kind of moderate aeration, say light use is fairly moderate. Then after 3 to 4 days, the rotifers will reach about 500 to 600 per milliliter. And just think of that again, remember those little tiny guys, at 5 to 600 in a little small milliliter, cubic centimeter. That's a lot. So then you're going to harvest them and feed them to the fish. or you can even use them to inoculate other tanks. So this is an example of some of the microalgae tanks. They're clear, you've got high quality light above and to the side usually. In this case, this is a big operation, right? You're raising different species of algae. And then you have, on the other hand, you can just purchase algae. This is a lot easier. It's a lot more expensive, right? I think most facilities are going to the packaged, or I mean the packaged algae, thanks. Yeah, it's just a lot easier to work with. Now, you can enrich the rotifers with omega-3 fatty acids. It's becoming pretty common. We use the same product, or a similar product that we use for the Artemia, which is a company, Celco, and it's loaded with DHA. And there are some others. Algamac is also pretty common in rotifers. And so we're going to enrich the rotifers for about 18 hours usually, anywhere from 8 to 18 hours. And again, what this does is this supplies the rotifers with plenty of lipid nourishment to make sure that the essential fatty acids are provided. This is just a breakdown. You're going to harvest the rotifers with different size sieves, depending on the size of the rotifers that you're culturing. Remember, we talked about the SS size, which is like super small, the S is small, and the L is large. And here's an example of a sieve. It's just a net, and you pour your water. You may have like a 10-gallon bucket, and you're going to pour the bucket with your rotifers into this mesh cloth, which is like a net, a fine net, and then you can slowly raise that up to the desired, to allow just the desired volume for you to go in, and you can dip out a quantity that you want to enumerate. It's really important to know the concentration and count the numbers, and then you're going to apply those to your culture tank. I'm not going to go through the probiotics. I think that's Ken right there. That's the guy who's gotten a little older since he's probably 7 or 8 years old. Okay, so let me go ahead. That gives you an idea. I know we're just barely kind of scratching the surface on this, but I just want to give you kind of a sense of how some of this stuff is done, because it's quite a bit different than what we find with other, feed development, feed production. I mean, this is not producing the feed at the feed mill, right? Again, from Harbor Branch. Now we're talking about Artemia. We've already talked a little bit about it, so you have an idea what we're getting ourselves into here. Where do these things live? Where do they come from? Well, they're all over the world. They're mainly in salt lakes. That's where they thrive. The Great Salt Lake supply in Utah and also the salt lakes in San Francisco are two of the best in the world. Okay? There are some in China that, because of natural industrial pollution, they're horrible, but they're sold all over the place. And I know when I was in Myanmar, which is over here, and then in Bangladesh, you would get these like cans. They're usually canned, and they'd say like Utah brand or Great Salt Lake brand Artemia from like someplace in China. Well, they were not like or Utah-based or Utah origin or San Francisco origin product, and the lipid profile and would not be nearly as good, and some of the other things like a prevalence of pathogenic bacteria and the low hatchability, those would be things that would often be fairly common for a culturist to experience with some of those lesser known and lesser quality products. and for cultures, it's really important. In fact, when you go to purchase the Artemia, one of the first things you're going to ask for is a fatty acid profile, and believe it or not, the companies will take a sample of the eggs, and they'll send it off for analysis, and they'll give you a breakdown of all the fatty acids. In addition, they will do an in-house hatch rate. So you usually can buy a product that has like 95 to 100% hatch, then a less expensive product would be like 87 to 95% hatch, and then there's one that would like the third level, like a C brand, might be 60 to 80% hatch. And depending on what your economic situation is, maybe you can afford the #1, the gold level, or the cheaper brand, right? But it's important to know what you're working with and what you're paying for. Again, life cycle of the Artemia, we've already talked a little bit about this. You start with the dry cysts, about the size of a pinhead, and then they're going to hatch after about 24 or so hours, depending on the temperature, into these nauplii. This is really what's critical for most of the feeding. After about 2 weeks, they're going to fully mature into the sexually reproductive, male and female, these adults. But the thing is, at this stage, they're so large and they're so devoid of any fat or lipid. They would, #1, they'd be too large for the larvae to eat. But #2, they wouldn't have the material in it that the larvae could utilize very well. So again, just showing here that in a few gallons of water, you can hatch 5 to 10 million of these Artemia nauplii. They're usually maintained at about 1 per ml of culture water. Again, as we've talked about, the newly hatched brine shrimp have the most nutritional value. After about, in fact, this is here, they lose their nutritional value after about 10 to 12 hours. Actually, if it's warm, after 6 hours, you can see dramatic change. The color will change from an orange to more of a yellow, and you can see also, instead of the whole nauplii being nice and plump, it'll start to elongate a little bit, and from the edge, you'll see kind of a clear zone where the muscle is starting to develop, and the lipid is no longer present because it's been used. After it's about 24 hours old, then you're going to start using that enrichment that we were talking about. Again, it's about the same sort of lipid that we use with the rotifers. There's a discussion about counting Artemia. Again, it's just done volumetrically. You'll get your batch, you'll pour whatever you think you're going to need to feed out into a net. You'll adjust it such that it's got a working volume that's fairly easy to enumerate from. Let's say 10 liters, right? 10 tens are you to work with, and then you'll get maybe a 1 liter container and pull that out, and then from there you can take your 1 ml and put like an ml on a dropper or on a slide, and with your dissecting scope, you can count how many Artemia are in that. Then you back calculate and figure out what your total concentration is. So let's just go ahead.
We may have to stop there, Mike.
What's that?
We're now at limit,
It's
it's 2:45, yeah.
Okay, so here's what I'm going to do. 2:45, okay, so we've got 10 minutes.
No, we're done.
Oh, we're done? Okay, so the bottom line here is there is a whole batch of cysts. You're going to add some chlorine. The chlorine will actually remove that sheath. The color is going to change from brown to orange. That means that the covering has been completely dissolved. And you're going to go ahead and incubate those in a cone. Then you're going to drain them into a net. And you're going to go through all that, encapsulate them, And you're gonna have all these millions of wonderfully nutritious artemia to feed to your wild fish.
Does anybody try and feed like pellets or anything as far as mill as opposed to live, or do the fry have to have live fish or
Well,
live?
there are some companies, there's one out of St. Louis called Odihini, it's been around, I think it was originally some extremely